Hi there. We're going to take a look at capacitors and see how they work in circuits. We learned about capacitors before in the electrostatic section. We learned what they are, we learned how they're constructed, we learned how they store charge and energy. Now we're just going to put them in circuits. And the good news is you kind of already know how to do this because they're really similar to resistors with some important differences. First of all, how do you find the equivalent capacitance of a series of capacitors? Well, if they're in series, 1 over the total capacitance equals 1 over each of the capacitors. This might look familiar because this is how we added resistors when they were in parallel. That means that it's the same exact process, but it's opposite. It's for series capacitors add this way, and then you can imagine for parallel, it's also going to be the opposite of what resistors do. The total capacitance in parallel, you just add them together. If you could do that which we did before, you're good to go. You just have to remember they're backwards. Now let's look at a simple circuit and do some equivalent capacitance. All right, let's take a look at this circuit right here. What we're trying to do first is find what's the equivalent capacitance of this circuit. If we were doing this with resistors, we'd find what the equivalent resistance of these two in parallel were, and then we would add it to this one because now that equivalent would be in series with that, and that would give us our equivalent resistance. Well, guess what? In capacitors, that's exactly what we do. We do the same thing, so the process isn't really different. The first thing I'm going to do is I'm going to find what the equivalent capacitance is of this 3 microfarad capacitor and this 3 microfarad capacitor. Now where it's different is that to do parallel, we just add them. So I could replace those two 3 microfarad capacitors in this circuit with a single 6 microfarad capacitor, which then winds up being in series with the 3 microfarad capacitor that's left. Now here for series, I have to do the funky 1 over thing. So I'll have the 1 over the equivalent capacitance equals 1 over 6 plus 1 over 3, which is equal to 3/6, which when we invert it becomes 2 microfarads. So that's my equivalent capacitance for this circuit. Same thing as resistors. It's beautiful. Now for the next part, what we're going to do is figure out what the charge and voltage is on each of these capacitors. Okay, you can see what I've done here is I labeled the capacitors, capacitor 1, capacitor 2, and capacitor 3, and I made a little chart down here. So one thing I know is that the total capacitance of this circuit is 2. Now I know it's supposed to be microfarads, but I'm just going to write the numbers without the units for the sake of ease, I guess. All right, and we know that the voltage for the whole circuit is 4. The relationship between these three is that the charge equals the capacitance times the voltage. So if I have 2 microfarads of capacitance for the whole circuit and 4 volts, that means I can multiply those together to get 8 microcoulombs of charge. Now here's where we got to be detective-like. This charge is going to come out of both sides of the battery. So charge is going to come out from the left side of the battery, come up here, and split itself onto those 2 plates. I could take a wild guess and say, hey, since they have equivalent capacitance, I bet you it splits it right in half. It turns out that's true, but if these weren't the same, you couldn't do that. So what we will do to confirm our wild guess there is see what happens on this side, because the charge is also going to come out of this side, so to speak. I know it really only comes out one side because electrons are the only ones that can really move, but let's just, for sake of understanding, pretend this. What we're going to do is we're going to see that all the charge that comes out of the battery has to go to this one plate over here. So that tells us that C3 is going to get 8 microcoulombs of charge. Now, what that's going to allow us to do is calculate the voltage on that. And so if voltage is charge over capacitance, that's going to be 8/3, which happens to be 2.66 volts. Just like in our resistor circuits, voltage gets split up in the same way. what you can imagine is that if this is a resistor circuit and these were resistors instead, you'd say, okay, well, this one's getting 2.66 volts. I'm going to write that here. Well, that means the rest would have to be on either this one or this one. You can use the same logic for capacitors. Even though we don't have charge moving all the way around through the circuit, it turns out that the total voltage in making a loop around the circuit is equal to the battery voltage, just like in resistor circuits. So that means that if this is 2.66, this one and this one will get the rest, which happens to be 1.33 volts each, and they're in parallel, so they have the same voltage. That same principle of voltage applies to capacitors as it does to resistors. Now 3 times 1 1/3 happens to be 4 microcoulombs, and 3 times 1 1/3 is 4 microcoulombs. So remember before we were saying, well, I have a feeling that if that 8 microcoulombs of charge comes out and splits itself amongst these two, it'll split equally. Well, there it is. 4 and 4 add up to 8. Now, if these numbers were different, you had a 2, a 3, and a 4, it would make different numbers, but the principle would still be the same. The thing that's different here, honestly, is that when you find this this charge for the whole circuit, you get to apply that charge to the capacitor that are in series with that battery. So from here to here, this one branch of the circuit, this capacitor is in series with the battery, so it will get the whole charge. Remember, in resistors, that's what would happen with the current. So it works kind of the same. It's not a current, but it is charge, and so you can use some of the same logic that you did to analyze resistor circuits, and that's cool. Makes your life a lot easier.